Hello, welcome to the fourth video of this series. It will be on oxidation today. So today there wouldn't be a non-technical summary because this topic probably wouldn't have much interest to non-technical audiences. So I will dive straight in. So what we mean by oxidation, obviously in this case, will be the oxidation of silicon, right? So oxidation of silicon to form silicon dioxide. So silicon dioxide is obviously a very important material in MOSFET architecture in the synthesis of integrated circuits on silicon chips. So here are some uses for silicon. So as you can see, of course, as you've covered in chapter 2, the second video, right, it can be used for like field oxides to define certain areas, right? It can be used as paired oxides, right? Especially like between the silicon and nitride layers, right? Because of the high stress between silicon and nitride crystal lattices. And it can also be used for the gate as a gate oxides. And at the same time, silicon oxide often exists as like a thin native oxide layer on silicon surfaces that have not been thoroughly cleaned or processed before a certain process step in fabrication. So it's important to bear in mind that fact as well. And these are thermally grown oxides, or oxides that are grown by this on the silicon surface, right, by consuming the silicon substrate itself, right. So it's oxidation in air or like oxygen containing atmosphere. And deposited oxides or dielectrics are things that are basically like layered on top of the silicon by reagents that are added to the silicon, right. So it's not consuming the silicon substrate itself. So normally these deposited oxides, these deposited dielectrics are used for like interlevel dielectrics, right, ILD. um, they are also high gate dielectrics are also a type of deposited dielectrics because they are often not based upon silicon, right, so they cannot be thermally grown by consuming the silicon itself. Okay, so let's briefly touch on the importance of having a nice oxide layer for the gate, for example. Okay, so as you know, right, this is your MOS structure, right? Your metal, or in this case, is polysilicon, but basically it's heavily doped such that it's a conductor of electricity, similar to that of metal. Then we have the oxide, then we have the silicon or semiconductor. So what this oxide does is that basically it acts as, in a sense, effectively a capacitor, the dielectric of a capacitor, and we do not want current to flow through it. So when there are defects and non-uniformity of the film, it tends to result in dielectric breakdown at these positions where there can be like macroscopic defects like pinholes, like scratches, or other forms of more microscopic structural level defects and non-uniformity. Right, and at the same time, we also don't want it to have any kind of traps, right, charge traps, right, which is basically like states that can trap certain charges in the oxide, as that would affect the reliability of the device as well. And of course, we also don't want any dopant penetration to the oxide, which I'll cover a bit later. So, in view of this, right, we need to understand what kind of defects can exist in the oxide layer. And so, considering like silicon dioxide deposited directly on silicon, right, let's cover first what kind of charges can exist in the silicon dioxide layer. So four kinds of charges are associated with basically these interfaces of the oxide and silicon material. So the first one is the fixed oxide charge. The second one is the interface trap charge. The third one is the mobile oxide charge, and the last one is the oxide trap charge. So basically, the existence of these charges in the oxide, because by right, technically, ideally, we want our oxide layer to be basically a complete insulator. So it does not carry charge, it does not transmit charge, right? So it's electrically neutral and completely insulating. However, in reality, right, there tends to be certain charge that can build up, that can accumulate, that can be created in the oxide layer, and that is it degrades device performance. Okay, so however, of course, different charges have different impacts on the eventual device performance. For example, like fixed charges, right, may not be that important, right? They may not be that degrading to the device performance. However, interface trap charge can affect device performance quite severely. So let's go straight into them. So let's look at fixed charges and interface trap charges. So for fixed oxide charges, it's located very close to the interface. So normally it's within 3 nanometers of the interface. And unfortunately, right, it is unchanged during device operation. So this is a fortunate fact. Why? Because that means that it always behaves in the same way. So it doesn't really impact device reliability. We just have to account for it once, and then after that it's done, right? It is always a fixed kind of factor to be considered. So it doesn't really degrade the device reliability that much. So it is always positively charged, and its origin is due to incomplete oxidation of silicon. So you can think of silicon as consisting of course, silicon dioxide to be consisting of silicon and oxygen atoms. So when it's incomplete oxidation of silicon, there are some silicon atoms in the SiO2 that's not bonded to any oxygen atoms. So these like terminal silicon atoms, right, take on a positive charge. Okay? So they take on a positive charge. And so this depends on the temperature used during the oxidation. So the higher the temperature of oxidation, the smaller the concentration of these fixed oxide charges, because at higher temperatures oxidation can go to completion more easily. And if you cool down faster or cool down in an inert gas environment, it prevents incomplete oxidation from happening as you ramp temperature down. And so that also reduces the concentration of fixed oxide charges. And the third way to reduce the concentration of these fixed charges would be to use a chlorine containing gas, which I'll cover later. It improves the oxidation process and the structure of the SiO2 that's eventually formed. So now I'll go through the second one, which is interface trap charges. So for interface trap charges, they are basically arising from dangling bonds. So this is an example of a dangling bond that has been like replaced with a hydrogen. But imagine the hydrogen wasn't there. Imagine the hydrogen wasn't there. So this silica atom is only like bonded, right, to two or three other atoms. And so there's a dangling bond over here. So you can think of the dangling bond to be somewhat like a radical, right? A single unpaired electron. So when a single unpaired electron is there, it can do two things, right? Firstly, it can attract another single electron to go together with it, and it form a lone pair. And that is the idea of trapping an electron, right? So the radical is there, the single unpaired electron is that it traps a free electron from somewhere. After all, you're applying some voltage, I presume, when operating the device. So it traps the electron, and then it becomes a lone pair, and that is considered electron trap. At the same time, right, if there's a electron acceptor somewhere, you can give off that, the radical can give off that single unpaired electron, and effectively what that does is that it's acting as a hole trap. Okay, so in that sense, you can think of these dangling bonds as energy states that are singly filled. So it can either be made complete by trapping an electron, or it can release the electron that it holds, right, and become a hole trap. Okay, and so because these energy states are within the band gap, so these traps can become positive or negative depending on whether it traps a hole or electron, and that depends on the applied potential on the device. If you apply a highly positive potential, it's more likely that, for example, maybe holes will be trapped. Or if you apply a highly negative potential, it's more likely that electrons will be trapped. Okay, so this interface trap charges has the same origin as your fixed charges, right? Basically, it's an imperfection or incompleteness of the oxidation process. So these two quantities, their concentrations are correlated. So the problem with having interface trap charges is that the channel mobility of the MOSFET device is reduced significantly. So you can think of mobility as how easily electrons and holes can move through the channel. So imagine if you have traps along the way, they can like trap electrons. That's like along a highway, you have, let's say, traffic police every few stations like stopping motorists to check their license to find them if they're speeding. So of course that will slow down the traffic, right? So it's the same thing over here, right? Mobility will be reduced when there's a lot of traps along the way in the channel. And at the same time, it also degrades the other device performance, such as the subthreshold slope of the device, because you can think, now with these traps, I need to apply a greater increase in voltage to achieve the same increase in current, because some of my electrons get trapped along the way, right? So that will increase the subthreshold slope. And one way we can reduce these interface trap charges is by using the forming gas anneal. So we anneal the interface, or basically the oxide and silicon layers, with a combination of nitrogen and hydrogen gas. So what is very important is that this hydrogen gas content, right, the hydrogen atoms can go to these dangling bonds and form a silicon hydrogen bond that basically passivates, right? It basically passivates the interface trap charges and removes or resolves this issue of interface traps. So I'll cover the next two kinds of charges. So one of them is oxide trap charge states. So oxide trap charges can be positive or negative. So it's due to holes or electrons that are trapped in the bulk of the oxide. So note that this is no longer at the interface region, but it's in the bulk of this oxide. So why do these trap states, or why do these trap charges, right, once they are charged, right, why do they occur in the bulk of the oxide? How do they occur? So it's normally caused by broken covalent bonds in the oxide bulk, and this can happen due to energetic processes that the silicon dioxide layer is exposed to. For example, ionization, right? Um, when you do ion implantation, right, the silicon dioxide is often exposed to the high energy ion beam, or maybe other energetic processes like involving the plasma, right? Plasma etch, plasma enhance deposition, things like that. Okay, and it can be annealed out once again by having a certain annealing treatment in hydrogen gas or in inert gas. So this can be annealed away. And as for the last one is mobile ionic charges. So this is caused by a contamination, right? Contamination by other elements such as alkali ions such as sodium, potassium, lithium, as well as also possibly negative ions and heavy metals as well. So this can enter the silicon dioxide in the processing stage because after all your oxidation furnace, right? A lot of times the walls or certain apparatus in the oxidation furnace are made of these metals. So there's a possibility of metal ions entering into the oxide layer during the oxidation process. So because these ions are mobile, right, so they can move when a voltage is applied, which is always the case during MOSFET, when you want to turn on the MOSFET, and so it can cause the threshold voltage to shift accordingly, and this will affect the device stability. Okay, so now I will cover basically the overview of thermal oxidation of silicon. So there can be two kinds of thermal oxidation of silicon. The first one is a dry oxidation where you're simply oxidizing the silicon in an oxygen environment. So this tends to occur more slowly. However, the oxide growth is of a high quality. So because of its high quality, it's excellent for gate oxides, which tends to be very thin, right? So we do not want a defect, a layer of oxide to be full of defects when you're using it as a gate. As we mentioned earlier, it can cause leakage, electric breakdown, so on and so forth. Right, it's also possible to add nitrogen in the atmosphere. They're oxidizing it to form oxynitrides. Okay, and so maybe one thing that I should let you know is that the mechanism of oxidation is that the oxygen, or in the later case for wet oxidation, the water, the steam, right, diffuses through the oxide layer and reacts at the oxide silicon interface, right. So it's not the case that silicon diffuse through SiO2 and reacts with oxygen at the silicon dioxide air interface. No, that does not happen. In fact, oxygen diffuses through the silicon dioxide layer and reacts with silicon at the oxide silicon interface. Now, how do we know that, right? Just for your information, we basically can know that by, let's say, growing the SiO2 layer using normal oxygen. Then we change the isotope of oxygen, and then we continue growing the silicon dioxide layer. And so we observe, right, I can observe that using, like, let's say, maybe some techniques, maybe NMR related techniques, right? I can observe where the layer of SiO2 that's formed from the different isotope, where it is formed, right? So because it was added later, so if that modified oxide, right, with a different isotopic concentration, right, is formed at the surface, then we know that silicon diffused through the oxide layer, right. However, we found that it is formed at the silicon and oxide interface, so we conclude that oxygen must have diffused through the silicon dioxide layer to react at the interface of the silicon and silicon dioxide interface, right. So the second kind of oxidation is the wet oxidation, also known as steam oxidation, where silicon is reacted instead with water or steam, basically, because it's in the gaseous state. So this occurs much faster. We'll see why later through the basically certain equations, right, why this is faster. However, it's of poorer quality because hydrogen is produced as a byproduct, and the hydrogen needs to escape. And when it escapes, it forms like tunneling channels through the oxide layer that can eventually, right, during device operation, also tunnel things like electrons. So it is less robust. It's of a less robust structure. So it's good for like things like fuel oxides or masking or things like that. However, if you have to use as gate oxide where there's a very stringent requirement of its electric properties and electric strength, then this is not so suitable. Okay, so one thing to take note is that oxidation always accompanies a volume expansion, and this is very intuitive because after all, you are transforming from Si to SiO2, right, which is right intuitively occupying a bigger space. And indeed, we can actually use the densities of silicon and silicon dioxide to calculate that basically there is a 2.2 times volume expansion. So basically, the silicon dioxide film has compressive stress because it's forced to, let's say, at the interface take on the same area as the silicon below it, but it has a need to expand its volume. So you can think of it as bearing some form of compressive stress at the interface. Okay, so now I'll cover the Deal-Grove method for oxidation kinetics. So I won't cover the derivation, I'll just cover the general idea of the model, because I think it's important to know the idea of the model to be able to appreciate the trends and the relationships that are introduced later. So let's say you have a certain source of gas. So let's say it's either oxygen or steam. So we know this concentration, right? Because it's, let's say, a setting in our machine. We want to infuse our wafers with this concentration in the gaseous phase of the reactor, of the furnace. Okay, so this is a known value. Then this gas will diffuse to the silicon dioxide surface and it will form a surface concentration. However, right, there is a difference between surface concentration and the concentration inside the oxide near the interface, because there is a certain solubility, right, solubility equilibrium between the gaseous phase and between oxygen in the gaseous phase and oxygen in the silicon dioxide lattice, right? There's a certain solubility equilibrium. Okay, so this is the idea behind these first two equations. So we can define basically our certain concentration, right? Our certain concentration C star as a function of Cg, right? Modified by basically the Henry's law constant. So this takes into account the solubility relationship of your oxygen or steam in the silicon dioxide material. Okay, and so we can define the first flux to be the flux, right, from the, let's say, from the furnace, right, to the interface and dissolving into the interface. So you can define this as to be the first flux. Okay, so it represents Cg to Co. But just that you modify Cg, right, with the Henry's law constant to consider the solubility equilibrium occurring at this interface. So that's the first flux. The second flux that occurs is from the interface of the silicon dioxide, already inside the silicon dioxide material, but close to the interface with air, to the interface with silicon. So it's a diffusion through the silicon dioxide layer. Right, and so you can use Fick's law, right? Fick's first law, where the flux, right, is proportional or is equal to basically the diffusivity times the concentration gradient. So we basically over here we assume a linear concentration gradient. Okay, and the last flux is a reaction flux. So it's basically O2. Let's just take it to be O2 for now. O2, right, reacting with Si and then in a sense disappearing, or not really disappearing, but being incorporated into the SiO2 layer. And so that is basically defined in terms of a first order rate equation, where is the rate of reaction, the third flux is effectively a reaction rate, is equal to the rate constant of the surface reaction times the concentration of your oxygen at the interface. Okay, so we do see that the second flux, right, it depends on how thick the silicon dioxide layer is, and later we want to solve for how the thickness varies in time. So we will expect basically a differential equation that we need to solve later. And yep, so we basically can solve these three sets of flux by taking the fact that in steady state, right, these three fluxes are equal. Because if one of them is unequal, right, there will be a balancing out of the system until the case where in steady state all three fluxes are of equal value. And so if we take that to be true, we can basically do your necessary mathematical manipulations and obtain this relationship of the thickness of the oxide layer over time. So you see this tau here, this tau is to take into account any previous oxide layer that was already grown. So this is quite common because let's say silicon surface exposed in air normally grows a thin native oxide layer already, right? So we put this tau here, right, to take into account any previous oxide thickness that has already been grown. So it's like basically a T naught, right, considering any layer thickness, right, that has grown in a hypothetical amount of time tau in the past. Okay, So you don't have to worry too much about this, but I just need to take a look at these two constants. So we can see that B, the constant B, depends only on diffusivity and not on the rate constant of the reaction. So you can think of this as a diffusion controlled term. And the other constant, B over A, depends on Ks only. Not the diffusivity, but the rate constant of the surface controlled reaction. So you can think of this as a rate controlled or surface reaction controlled term. And so it turns out that when there's a thin oxide layer being grown only, that means X naught is small. So normally this is when you're growing the oxide for only a short time, so only a certain amount of thickness is grown, right? We realize that the square term, right, becomes less significant than the term involving only X naught to the power of 1. And so we basically can only consider this term, right? And when we only consider this term, we see a linear relationship between X naught, the oxide thickness, and time. And the constant, right, of this relationship is a surface reaction dependent constant only, not dependent on diffusivity. So you can call this the surface controlled regime. When your oxide is so small, the diffusion time through the oxide is negligible, and what really determines the rate of oxidation or the rate of growth of the oxide layer is the reaction occurring at the interface. Okay. However, when your X naught becomes larger and larger, we realize that the square term dominates, right? The square term dominates. And so we can simplify this equation, right, to consider only the square term, and we see a relationship dependent only on the other constant B, which is dependent only on diffusivity. So you can consider this a diffusion control regime. And intuitively, this is because in this regime, the oxide layer has grown so thick that is no longer the surface reaction that controls the rate, but the long diffusion time it takes to diffuse across the oxide layer that controls the rate of the oxidation process. And so we can define, let's say, an intermediate range when, let's say, your Ks times X over D, right, this term over here, if we take it to be approximately equals to 1, that generally we can use it as a rule of thumb to think of it as a transition regime or point of transition between the surface reaction control and the diffusion control regimes. So the surface reaction control regime is sometimes called a linear regime, the Dilgrove linear regime, because it's a linear relationship, right? And as for the diffusion control regime, it's often called the parabolic regime because it follows basically a kind of parabolic relationship, right? Squared. There's an X squared term over here. And so let's take a look at the temperature dependence of B and B over A. So we can see that both terms, right, take on an Arrhenius kind of relationship, right, because temperature both enhances the reaction rate and also diffusivity, right, and the reaction rate and basically rate constant and diffusivity are both dependent on temperature according to an Arrhenius kind of relationship. And so we can see that basically when we use, right, H2O, we see that basically there is a much lower activation energy for the constant B, which is basically the diffusion control constant. And at the same time, right, we see that B over A, right, we see that the pre-exponential term is also much larger. So we see that basically the switch from dry oxygen to a wet oxidation using H2O will enhance both the constant B and the constant B over A, right? And so what is the reason for this, right? This is because water, when it is used for oxidation, or steam rather, steam has a much larger solubility in oxide compared with oxygen, right? So the Henry's constant H is much larger for steam compared to oxygen. And if you look at the expression for both B and B over A, we see that C star is appearing in both expressions, and H, the Henry's law constant, appears in C star. So we conclude that the Henry's law constant appears in both B and B over A. So when the Henry's constant is higher for steam compared to oxygen, it will enhance both oxidation in the linear and the parabolic regimes, as seen from how, right, basically the expression becomes more larger in value, right, for both B and B over A when you switch from dry oxygen to steam. Okay, And however, as mentioned previously, the oxides grown in wet oxidation are less dense, right? Because there's a certain out diffusion of hydrogen gas that occurs. Okay, and so therefore, wet oxidation is typically used when a thick oxide is required that will not be subject to any significant electrical stress that can lead to a dielectric breakdown of the material, right? And as for dry oxidation, is as in converse, right, obviously it is slower, however it is of higher quality and therefore can be used as the gate oxide where it is subject often to basically high electrical stress and there's a stringent requirement for its electrical performance. So let me go through briefly certain factors affecting the oxidation rate. So the first one is of course pressure, right? Very intuitively, a high pressure would increase the oxide growth rate by increasing the linear and parabolic rate constant. So that is both B and B over A, right? And this is because, right, an increase in pressure will increase the partial pressure of your oxygen or steam, and that will increase your value of C star, which is present in both the B and B over A expression. And yeah, so there's also a dependence on crystal orientation, right? And this is basically only affecting the surface control regime, so which is the linear regime. And that's because the interface reaction rate constant Ks depends on the crystal orientation, where the basically the linear constant B over A is higher in the 1 for the 111 surface of silicon compared to the 100 surface of silicon. So the reason for this is very intuitive, because the 111 phase has a larger basically planar density of silicon atoms than the 100 phase. So when you have more atoms exposed in your 111 phase, obviously the chemical reaction will occur at a faster rate, right? Because you have more sites at which the chemical reaction can occur that's exposed to the reagent, which is oxygen or steam. However, the parabolic rate constant, right, which is the diffusion controlled rate constant B, is not dependent on crystal orientation because it only depends on diffusion through the oxide layer, which does not seem to have a significant dependence on the surface of silicon that's exposed. Because after all, regardless of what silicon surface exposed, the silicon dioxide layer grown on top of it will be amorphous anyways, right? And so the diffusion through that layer will not depend much on crystal orientation of the silicon below it. And thirdly, the oxidation rate also depends on the surface geometry, where we realize that oxidation tends to be slower for convex and concave corners, right? And normally, the smaller the radius of curvature, that means the more dramatically sharp the features are, the slower the oxidation. And so this is often a problem for lower temperature oxidation, because at higher temperatures, the oxide has a certain amount of basically a viscosity that allows it to flow to fill these non-uniformities better. So one more thing to take note is that the dopants present in your silicon can also affect the oxidation, right? And so the common dopants for silicon all tend to enhance oxidation rate when present in the substrate in high concentrations. This is because these dopants, right, they distort the lattice structure of silicon, right? Because oftentimes when they insert themselves into the substitutional sites, they have a different radius, tends to be either larger or smaller, right, than silicon, and this difference in the radius will result in a certain strain in the silicon lattice. And so when you have a strain in the lattice, you have a weakening of the silicon bonds, and when you have a weakening of the bonds, it makes it easier for the chemical reaction to silicon dioxide to occur. And so the oxidation rate of course will depend on the dopant concentration in silicon dioxide for diffusion control oxidation. So when we have more dopants in the silicon dioxide, it can, let's say, enhance certain diffusion through the silicon dioxide, and this is especially important for oxidation that is in the diffusion control regime. Whereas for the surface reaction control regime, right, what affects it is the dopant concentration at the silicon surface, because that's where the surface control reaction occurs, obviously. So one example that we can use as an illustration is phosphorus. So phosphorus tends to pile up at the silicon surface, and this will lead to more vacancies in the silicon lattice structure. And because this oxidation process is enhanced by these spaces or these vacancies, right, the oxidation rate is basically enhanced in the reaction control regime. And we do observe that the linear rate coefficient increases rapidly when the surface doping level is greater than basically 10 to the power of 20 per centimeter cube, resulting in an increase in the oxidation rate. However, we only see a modest increase in the parabolic rate coefficient, which shows that even when phosphorus is present in the silicon dioxide layer, diffusion through it is not really affected or accelerated that much. So one thing to note is that when we grow an oxide layer, right, the dopants that's present in the silicon below it can redistribute into the oxide layer. So we can define a segregation coefficient that basically tells you at equilibrium what is the ratio of the dopant concentration in silicon to the dopant concentration in silicon dioxide. So in the case where this m is less than 1, when this m is less than 1, it means that the dopant prefers to exist in the oxide. That means at equilibrium, the dopant concentration in the oxide layer is higher than the dopant concentration in the silicon layer. So if the diffusion of the dopant through the oxide is not that fast, right, eventually a lot of dopants accumulate in the oxide layer. However, if the diffusion of the dopants through the oxide layer is fast, then what happens is that these dopants will be released into the air or into the environment, right? And when it's released into the environment, we see a dropping off of the dopant concentration that happens both in the oxide and also in the silicon layer below it. Okay, and in the case where the oxide rejects the impurity, which means m is greater than 1, that means at equilibrium, the dopant's concentration in the silicon is greater than the dopant concentration in silicon dioxide. So if the dopants don't diffuse through the oxide very fast, right, then there's pretty much not much of an issue, right? That there's a low dopant concentration in the oxide, and there's a bit of a build-up of basically dopants on the interface at the interface between the silicon and the oxide on the side of the silicon. And when, however, the dopant diffuses rapidly through the oxide, right, there can still be a drop off of the dopant concentration because these dopants are released into the atmosphere or into the environment. Okay, so I'll also cover what is the effect of chlorine on oxidation. So it is experimentally observed that the addition of 1 to 3% of chlorine-bearing species to the oxidation environment leads to a faster oxide growth and the observation of an increase in both the linear and parabolic rate constants. And so this can be explained by chlorine acting somewhat as a catalyst. So we note that the bond energy of silicon and oxygen is 4.25 eV. Right? However, that of silicon and chlorine is just 0.5 eV. Right, and this is actually also a principle that is exploited during during certain etching of silicon also, by the way. But for now, we just look at the case of oxidation. So we see that the silicon chlorine bond is much weaker than that of the silicon oxide bond, oxygen bond, and so basically we can deduce a mechanism where chlorine reacts first with silicon to form this SiCl bond, which is weaker, and that is easier to react and transform to the SiO2 kind of structure when oxygen is present in the environment. And so the result of this chlorine catalyzed oxidation is that we have a cleaner oxide with less metallic contamination as well, since chlorine is also conveniently able to react with many heavy metal atoms to form volatile gases, volatile metal chlorides. And so we see that conveniently not only does it enhance oxidation rate, it also leads to a cleaning of metal elements out of the oxide. In addition, we also observe an enhanced dielectric strength, a reduced oxide density, and an improved silicon-silicon dioxide interface, right, with a lower interface state density. So an overall improvement in the structure and the defect concentration in the oxide layer. And so the chlorine species that we can use for this oxidation process can be, of course, your standard anhydrous chlorine gas, right? It can be hydrogen chloride, it can be trichloroethylene, or it can be trichloroethane. So it can be a range of different chlorine containing species. And so now I'll briefly cover a thermal oxidation method. So the most straightforward method is through the use of a furnace. Right, so in the case of dry oxygen, you can pump in oxygen and nitrogen gas. In the case of wet oxidation, you can pump in steam. However, it's more popular nowadays because it's cleaner to pump in hydrogen and oxygen, which will then react to form steam in the furnace. So the good points of this kind of thermal oxidation is that it's inexpensive, it's able to achieve excellent temperature uniformity and therefore a good thickness uniformity throughout the wafer. Right, however, the problem is that there's a high thermal mass, so it takes a long while to heat up. Right, so it leads to long process times, which makes it more suitable for growing thicker oxide. And it's not good for growing ultra thin gate oxides, which requires a very rapid and fast application of heat to achieve a very thin layer of good quality oxide. And so therefore, right, for the case of ultra thin gate oxides, we need to use this idea of rapid thermal oxidation. Right, rapid thermal oxidation, where we use basically halogen lamps. So this kind of setup has a low thermal mass. Okay, low thermal mass, so it can be able to achieve short process time and achieve rapid heating. So if you were to use the conventional kind of thermal oxidation for gate oxides, right, to achieve less than 30 angstroms, because you cannot heat very fast, right? So we need to perform this oxidation at a lower temperature because we want to grow a thin gate oxide more slowly. However, that also has its own problems because at the lower temperature, the oxidation process is less complete. So it increases basically interfacial roughness at the silicon and oxide interface, and that will reduce the channel mobility. So basically, rapid thermal oxidation is able to mitigate this because it's able to reach high temperatures under very short time. So you can use higher temperatures without worrying about over oxidizing because our time of this heating application is very short. And also because of this very short heating duration, it also reduces the redistribution of any dopants in the silicon layers below the layer that we want to oxidize. Right? However, it's important to also note that the kinetics of oxide growth in this kind of setup, right, it tends to differ from conventionally grown oxide, and one possible reason is that basically this we're heating by lamps, and so lamps basically release like photons, and so photons can trigger basically your excitation of electron hole pairs in your silicon, because after all it is a semiconductor, and that could also play a role in the oxidation mechanism. So it's basically much more complex than the dew growth oxidation method, dew growth oxidation model that we saw earlier. And so how is thermal oxidation actually conducted in practice? So it's very important that we first clean the wafers, right? Clean the wafers with something called RCA clean, which I think I'll cover in a future video on wafer cleaning, right? Secondly, right, you have to put your wafers in the bowl, load it in the furnace, and when you ramp up the temperature, it's important that you ramp it up in the nitrogen environment because you don't want oxidation occurring at the intermediate temperatures you pass by when you're ramping up. Because oxidation at intermediate temperatures will result in incomplete oxidation that can result in interface states and trapped charges. So you want to ramp it up in an environment that's not oxidizing, which is like in the nitrogen gas, for example. Then we stabilize it, and then we pump in the oxygen gas or the steam to oxidize it. Then after that, we stop the gas flow, we anneal in nitrogen, and then when you ramp down the temperature, we ramp it down in the nitrogen environment again. Okay. And so now I'll just briefly remind you that, however, even though I mentioned very often SiO2 for gate oxides, right? Most companies have already moved beyond SiO2 for gate oxide and instead have turned to high K dielectrics. So it turns out that in many cases we want a high gate capacitance. However, because of the formula of capacitance, to achieve a high gate capacitance with a fixed, let's say, dielectric constant, let's say if you're using silicon, you are dealing with a fixed dielectric constant. So the only thing you can do is to decrease the layer thickness, right? But when we decrease the layer thickness to thinner than 1 to 1.2 nanometers, right, what happens is electron tunneling can occur, right? Because quantum tunneling effects occur basically at very much higher rates when the thickness of the barrier becomes very thin. And so this results in tunneling currents that are too large to meet the standby power requirements in most applications. That means your transistor is turned off, right? It's turned off, so it's on standby mode. It's not turned on. However, right, there's a still current in the off mode that's still flowing. So you can imagine like your handphone, right? It's turned off, right? It's on, basically it's on power, it's on like standby mode, right? However, it's continually draining power, and that's not desirable for any electronics, especially for electronics like the handphone, right? Where you don't want it to run out of battery too quickly throughout the day, right? So the alternative would be to use a material with a higher dielectric constant. So with a higher dielectric constant, we can still achieve a pretty good capacitance even with a higher thickness, a larger thickness, right? And so one material that's been used is hafnium dioxide, HFO2, right, which has a higher dielectric constant. However, we may want to use even better materials, right, like tantalum or like titanium dioxide. Right, titanium dioxide looks very tantalizing, right, because it has a high dielectric constant. However, the problem is that oftentimes as your dielectric constant increases, your band gap decreases. So what happens if your band gap is too small? If your band gap is too small, the material will not be very insulating. That means if you apply a large enough voltage, it's possible that the material can undergo dielectric breakdown, right? Undergo dielectric breakdown and become and create a path where electrons can conduct through the gate oxide, which is not desirable because it results in the gate leakage current. Okay, so most industry has settled on HFO2 as a suitable high K dielectric for the gate oxide. However, it's to be noted, and you can read that this in research papers that's available on Google Scholar, that the interface between the direct interface between silicon and HFO2 is not a good interface, with a lot of formation of dangling bonds. And as I mentioned earlier, dangling bonds can act as charge traps, which degrade the mobility of charge carriers through the channel. Right. So what is the solution? It's actually quite simple. It's silicon, then a layer of silicon dioxide, and then you deposit your hafnium dioxide. So it turns out that way the interface between hafnium dioxide and silicon dioxide is still acceptable, and the interface between silicon dioxide and silicon is of course acceptable. And so that's how they mitigate this issue of the interface trap states. And so that marks the end of the oxidation video. So in the next video, I will cover a very important and much more, I would say, complex topic, which is on doping and ion implantation. So yeah, hope you enjoyed this video and hope you enjoy the next one as well.